So, hello everybody, welcome to session 18 of ITCS 2020 about algorithms. So we will have 5 presentations in this session. The first one will be by Jalani about probing minimize. So Jalani, feel free to go.
Thanks for the introduction, Xue. I'm Jalani. I'm a 4th-year PhD student at CMU, and I'm here to talk about probing to minimize, a project on stochastic probing, which is joint work with my advisor, Weina Wang and Anupam Gupta. So I've been told that it's best to start things off with a concrete example, so I'll be doing just that. Imagine you're building a pool and you need a high-quality bag of concrete. So you go to the hardware store and you see what's available. It turns out there are 2 concrete brands available at the store, a trusted brand and a risky brand. Now you'll recall that I said we want a high quality bag of concrete, and we'll measure that quality in kind of a negative way. Each bag will have an independently random number of defects, where the distribution of defects depends on the brand. So for example, the trusted brand has defects distributed this way, and the risky brand has defects distributed this way. Now, naturally, each brand also prices their bags differently. The trusted bag costs $100, while the risky brand costs $20. So the problem is, given that you have a budget of $100, and your goal is to minimize the expected number of defects in your best bag of concrete, what should you do? Well, what can we do? In this case, we actually only have 2 options. We can either buy 1 trusted bag or buy 5 risky bags, right? And the expectation is actually pretty easy to compute in this case. If we get 1 trusted bag, then the expected number of defects is 3.5. Whereas if we buy 5 risky bags and take the best one, our expected number of defects is 1. Okay, and so in this case, we actually gain something from taking all of these risks. So now that we have that concrete example in our minds, let's go to the formal setting. So in general, this is going to be a dynamic set selection problem. So let me just say that we'll call our selection set S. Right? And we'll be choosing the selection set S from a universe U of indifferent elements. And for each of those elements, we're going to associate a random weight, which takes values in the integers from 0 to n. Okay, and so why do we have that? I'll talk a little bit more about why we have that restriction later. So we're choosing our set S, and our goal is to minimize the expected value of some objective function f, which is some function of the weights in S, right? And we'll write that as f of S with the understanding that, the weights there are implicit. So we can't just choose any set that we want. We also have some collection of feasible sets that we can choose, script f, and we'll require this collection to be subset closed. So for example, this could be like a knapsack constraint or a matroid constraint or anything like that. Okay, so again, our goal is to minimize the expected value of this function subject to constraint that our final set is within this feasible set. And we also need to distinguish between 2 different settings here, the adaptive setting and the non-adaptive setting. In the adaptive setting, we build our selection set element by element, and as we add an element to our set, its random weight is revealed, and we can then adapt our strategy based on it, right? Whereas for the non-adaptive setting, we have to choose our selection set all at once, and information is revealed at the end. Okay, right. So now that we have our formal model, what's known about this, and as a preface, we'll be focusing on the adaptive setting here. Okay, so what's known for adaptive maximization? Okay, you can think of it as like a beautiful, bountiful forest. Like there are a ton of results for adaptive maximization, whereas for minimization, it's more like a desert. Not much is known, even for some very basic objective functions. For example, if we take our objective function to be the minimum weight element in S, really nothing is known about the adaptive case. So what about the non-adaptive case? Well, everything we know is from one paper from Guha and Monagala in 2010 called How to Probe for an Extreme Value. In that paper, they give results for the non-adaptive problem, and they show that it's actually NP hard to approximate the objective value within a poly-m factor without sort of softening our budget constraint. And so we really need to be able to go over budget in order to approximate this well. Okay, and so along with that hardness result, they give an algorithmic result. They give a non-adaptive algorithm, which is epsilon close to the non-adaptive optimum, and which uses like log m times the budget. Okay. Now, they also left adaptive approximation as sort of a challenging open problem in this paper, and that's what we're going to focus on here. And so one simple question that one might ask is it possible to kind of close the loop and say, okay, the non-adaptive optimum is close to the adaptive optimum? No, it turns out. There are examples where the adaptive optimum is arbitrarily smaller than the non-adaptive optimum. And so you really need new techniques here. Okay, so what's the main difficulty in finding these approximations? Well, in particular, why is the adaptive case so much harder than the non-adaptive case? Well, we think that it comes down really to the optimal structure of the problem. In particular, like if we look at the non-adaptive optimal policy, it's just some set. It's possibly a difficult set to compute, but it's just some set at the end of the day. Whereas in the adaptive case, in general, the optimal adaptive policy is some m-ary decision tree, where m is the number of possible values that a random variable can take on, right? And so there's a decision tree that sort of depends on every single weight outcome, right? And so you might ask, why isn't this an issue for maximization? And that's because actually maximization, it seems like you don't need to be as concerned with what's happening in all of the decision tree, because in the failure cases, like things sort of happen in a nicer way. So let me be more specific. When we're doing maximization arguments, we can usually say, just like, for example, in the green part of this decision tree, like something good happens and we, with like reasonable probability, like get something close to the optimal objective value in this case, right? And any case where, something good doesn't happen, we can just say, oh, we get no objective value in that case and we'll be fine, right? Whereas when it comes to minimization, actually, we're very concerned about what happens in these worst cases, because often that can be the source of most of our expected value, right? So we can't just ignore that. We can't just chalk it up to, we can't just get like this factor in there, right? So how do we get around this difficulty? We use a technique that we call thresholding. And doing this, we can avoid thinking about m-ary decision trees entirely. We can focus totally on binary decision trees, but the catch is they're the optimal decision trees for an adaptive probability minimization problem, right? And I might be scaring you saying that we're going to do adaptive probability minimization, but let's go through an example of why that's not actually that scary, right? So intuition for what we call threshold problems. Let's go back to our concrete example. What if instead of wanting to minimize our expected number of defects in our best bag, we just said, okay, if it has fewer than 5 defects, then it's good enough, right? And now that we've said that fewer than 5 defects is good enough, let's just try to minimize the probability that our final bag has more than 5 defects, right? This 5 is going to be our threshold, and this problem is our threshold problem. Right? And you'll see this really kind of transforms our problem, because now, whereas before we were concerned about like all the m different possible values that a random variable could take on, now we're really concerned only about one thing: is it smaller than or greater than 5 defects, right? And so this basically turns our random variable, which in general is very complex, into a Bernoulli random variable or a coin flip. Okay, and so we can do this, and say we succeed, say we get something that has fewer than 5 defects. What if after that we shoot for something that has fewer than 2 defects? And what if we continue this process, right? We show 2 things about continuing this process, right? The first thing we do is we show that you actually can approximate some of these threshold problems well. And I won't go into how, but you can see that in the paper. The second thing we show is that you choose the right thresholds and you stop at the right time. This actually gives you a fairly good adaptive approximation. Okay, and so the results we get are, we close that open problem that I mentioned before, and we're also able to deal with a generalization of it, where instead of looking at the smallest weight in S, we look at the sum of the smallest k weights in S, and we get similar approximations Now, the threshold problem in this generalization is a lot more difficult, but after some work, you can approximate it. So besides this, in our paper, in the archive version, we treat two other variant, and I think we're probably about out of time right now. So I'm just gonna thank our funding sources and open the floor for questions.
Yeah, please feel free to unmute yourself or leave your question in the chat box. Yeah. So let me ask one question, Jalani. I just wonder, so you mentioned so the approximation algorithm has to violate the constraint by a polynomial factor, otherwise you get no constant approximation. But is that a log m term necessary, or we can expand something better?
So we've been wondering the same thing, right? Especially since we get the same log m factor, both, well, like Guha, Gohel, and Munagala, they got that log m factor. And then we got, in our adaptive approximation, for an entirely different reason, that same log m factor. So we're definitely wondering the same thing, whether there's some kind of fundamental barrier of log m or not, but we don't really have any idea of how to approach it.
Okay, thank you. Yeah, we got one question in the chat box. Can you see it?
Yeah. I start the fact that MIM problems are a lot harder to understand than Max was, also seen to appear in other areas. Yeah. It's definitely a common thing along a lot of areas. Minimization is just harder than maximization a lot of the time.
Yeah, we have. Okay, maybe that's all. Let's thank Jalani again. Okay. Okay. So. So the next talk will be. Okay. So Alexander, do you want to share your screen?
Yeah.
Okay. Okay. So let me make the introduction. So hello everybody. So the next talk will be by Alexander Lindermayr about double coverage with machine learned advice. Okay. Alexander, please feel free to go.
Yeah, thank you very much. Hi, I'm Alex. I'm from the University of Bremen in Germany, and I will present you joint work with Nicole Megow and Bertrand. And the goal of this presentation is to give you an idea on how we can improve a very classic online algorithm for a very, very fundamental problem using machine learned predictions. So first, let me introduce the problem, which is the online K-server problem on the line. So let's consider some real line. And the first part of the input is an initial server configuration, which tells us where our K servers are located in the beginning. So in this example here, we have just 2 servers located at C. Then the second part of the input is a sequence of n requests of points on this line, which arrive one by one. Meaning in the beginning, an algorithm just sees the first request, and it first has to serve it by moving one server to the request, and then it sees the next request, and so on. So the algorithm has always to decide how to serve the requests. And the goal is to serve all requests while minimizing the total travel distance over the whole instance. And we analyze an online algorithm using the framework of competitive analysis, where we say that an algorithm is alpha competitive if we can bound its cost by alpha times the cost of an optimal solution for all instances. And the optimal solution has, of course, access to all the requests in advance. So it is known that any deterministic algorithm is at least K competitive for the online K-server problem on any metric space, and therefore also on the real line. But on a line, there actually exists a very nice and classic algorithm called double coverage, which achieves this optimal competitive ratio of K. And it works as follows. So whenever a new request appears, it moves the at most 2 closest servers of the request towards the request with the same speed, and stops both when one of them serves the request. So this means that the closest server will eventually serve the request, and our closest server on the other side will move the same distance. Okay, now our goal is to design a learning augmented online algorithm for the online case server problem on a line. So what we have seen so far is an online problem with some online input, with sequence of requests. And we've also seen a classic online algorithm like double coverage, which solves this problem. And this algorithm has a competitive ratio, which means that it is robust against any input. But the thing is, it maybe performs poorly on easy instances or in special scenarios. Like in scenarios where, for example, an online input appears on a daily basis. There we could actually use a machine learning model, which we could train on this online input to gain some prediction on a solution or on the online input. So this could give us valuable information, but we have no guarantee that this information is really good. Because, for example, on one day, there could be a completely different online input. So the idea of learning augmented online algorithms is to combine the best out of both worlds here. Meaning we give the algorithm a prediction of a certain quality, but we also use the classic robust methods. And yeah, there are two special performance indicators which are interesting. The first one is consistency. And this is really the case where we assume that the algorithm gets a really good prediction, a perfect prediction. And so we say that an algorithm is alpha consistent if it is alpha competitive for this case, and this alpha should be really low. So we really want to benefit from having good predictions. But on the other side, we also want that our algorithm is still robust against any input, meaning it should be better competitive for any prediction. So this is a very successful framework and a very active research area, and there are like coming daily results for various online problems, but also in other areas of online optimization. Okay, and now we want to apply this framework to our problem. So let's first define a prediction model. And our prediction model gives us for every request a corresponding server which should serve the request. So when a new request arrives, the prediction model tells us, well, use this server to serve this request or use that server to serve the request. And based on this prediction, we can define a very simple algorithm which just follows the prediction, right? So if a new request arrives and some server on the left, which is in circle green here, is predicted, we just move the closest server, which is on the same side as the predicted server, to serve the request. So this means that this algorithm fully trusts the prediction. And if the prediction is correct, so if we kind of predict an optimal solution, we also follow the optimal solution, meaning that we are one consistent. But there are instances and predictions where this is just a bad idea and we get an unbounded competitive ratio. So we are not robust. But we've also seen another algorithm, namely double coverage. So if we give double coverage a predicted server, it will just ignore it. So it doesn't trust the prediction at all, and it just does its usual stuff. And since it is K competitive, we know that it is K consistent and K robust. And now what we eventually want is an algorithm where we can set our level of trust. So we want to set how much we actually trust the prediction. And our solution to this question is that we can balance this trust using different server speeds. And we came up with an algorithm which we call lambda DC, which works as follows. So whenever a new request arrives, we move the server which is on the same side as predicted server with speed 1. But the server on the other side with a lower speed lambda, where lambda is our hyperparameter, which is a value between 0 and 1, which expresses our trust into the prediction. So if we set lambda to 0, our algorithm just does the same as just following the prediction, which means that we fully trust the prediction. But if we set lambda to 1, our algorithm is just the same as double coverage. And yeah, for all lambdas in between, we kind of interpolate between both. And yeah, we can see this also in our theoretic results for this algorithm. Namely, we prove that this algorithm has a competitive ratio of at most alpha k, which is the consistency ratio, times 1 plus the quality of the prediction divided by the cost of an optimal solution. So this term just gets worse as the prediction gets worse, and the robustness ratio. So let's look at how these concepts look like. So for only having 2 servers, our algorithm is 1 plus lambda consistent and 1 plus 1 over lambda robust. So our consistency really interpolates between the consistency of following the prediction, which is 1, and double coverage, which is 2, depending on lambda. And the same goes for robustness. We are too robust for lambda equal to 1. And as lambda gets smaller, the robustness just explodes. And yeah, this generalizes also to general values of k, where we can get this expression for the consistency, which is, for example, for k equals 4, this is 1 plus 2 lambda plus lambda squared. And yeah, robustness is just we sum over the flip powers of lambda. So this is consistency and robustness, and we also have different error definitions, which look as follows. Yeah, which essentially just compare the cost between follow the prediction and an optimal solution. So that's how we measure our prediction. And further results of our work are a best possible consistency robustness trade-off among all memoryless algorithms that satisfy a locality property, which means that any memoryless algorithm which is in range of a factor 2 of our consistency has to have at least the robustness of our algorithm. This is a kind of lower bound. And we also validate our theoretical findings in empirical experiments, which really show that, for example, if we compare the green lines here, which are the lines where we just fully trust the prediction. So here we can see that the performance really gets worse as the prediction gets worse. But if you just add a little bit of non-trust, like setting lambda to 0.1, our algorithm performs really well, even for large prediction errors. Yes, so thank you very much. And now I'm happy to answer your questions.
Hi Alex, maybe I have one question. So in this slide you mentioned like this is the best possible trade-off up to a factor of 2 for some locality properties. Can you spell out what is the locality property?
Thank you for the question. This is mainly a technical assumption for our lower bound. And we call this property locally consistent. And this requires an algorithm to have a good performance for a sub-instance, which it just serves on a certain subset of servers. So if it just uses a certain subset of servers, it should have the corresponding consistency ratio depending on this number of servers for a certain part of the instance.
I see. Quality. We also have one question in the chat box. So it's by Omar Weissman. So he wondered if the results or insights can be generalized to general matrices.
Yes, thank you for the question. So we have some intuition on how this similar algorithm may work for tree metrics, because there also the double coverage algorithm is k competitive. But for general metrics, I'm not really sure how the speed approach could help. Maybe it helps for a small number of servers, but yeah, so I don't have much intuition there.
Okay. Okay. Yeah. Okay. Thank you for the talk, Alex. Okay. So let's go to the next talk. Yeah. Okay.
Hi. Can you see my screen?
Yeah. 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 It's good. Do you want to make it full screen? Yeah. Yeah. Pretty good. Yeah.
Thanks.
Okay. Let me make the introduction. So hello everybody. So this is the third presentation of our session by Sílvia about faster sparse matrix inversion and rack computation in finite fields. Okay. Okay. Sílvia, it's your turn.
Thank you. So my name is Sílvia Casacuberta, and I will be talking about faster sparse matrix inversion and rank computation in finite fields. And this is joint work with Rasmus Kyng. So let me begin by just mentioning, the two arguably main problems in linear algebra, which are that of linear system solving and matrix inversion. So to begin with, we have a clear relationship between these two problems. Namely, if we directly compute the inverse, then we have a solver for linear equations in A. Moreover, it was already shown in the 60s by Strassen that we can reduce matrix inversion to matrix multiplication. So that means that we have algorithms to invert the matrix and to solve a linear system in time O of n omega, where omega denotes the exponent of matrix multiplication. Now, these runtimes in linear algebra can be misleading when we work in finite precision arithmetic if we're not careful enough with the bit size. So it's known that Gaussian elimination is not stable in finite precision arithmetic, and neither is conjugate gradient, in which if we take the bit sizes into account, then this incurs a whole other factor of n in the runtime. So what can we do? Well, for example, there's no instability in finite fields. So for example, z modulo p, there's no round of error. And in that case, this provides a simpler setting for developing fast linear algebra algorithms. But also there's an interesting interplay between algorithms in finite precision arithmetic and those in finite fields. And it's beneficial in both directions. So there are instances of algorithms that were developed in the reals and that adapted in the finite fields, or we first develop them in finite fields and then we make them numerically stable. So that's to motivate why we care about these algorithms occurring in finite fields. So we can put in a table what are the current fasted runtimes for the two problems I mentioned, linear system solving and matrix inversion, in their sparse versions. And we compare the finite field setting with the finite precision arithmetic. One interesting open problem that was open until last year was whether or not you can solve sparse linear systems faster than matrix multiplication in the finite precision arithmetic setting. And that was answered in the positive by Richard Peng and Sandeep Impala and improved by Zipeni this past year. But it's still an open question to know whether or not we can also beat matrix multiplication time in the problem of sparse matrix inversion. So that's to give an overview of these types of questions. And now I'm going to focus on this cell, which is the runtime that we improve. So namely sparse matrix inversion in finite fields. And now I will give a brief overview of the construction of how we improve, how we obtain this runtime. So we begin by following the setup of Ebrahimnejad et al., which is the algorithm we improve upon. And following their setup, we introduce blocks. So the input matrix A has size n by n, but to obtain better runtimes, we introduce blocks, which are of size s by s, and then we have m of them, so that matrices are still size n by n. And then they introduce a block vector u, which consists of the identity matrix s m times. And basically, they use this block vector u to build two Krylov matrices with the input matrix A. So these block Krylov matrices are obtained by successively applying A to vector u. Okay, so you might be wondering, why are we defining those? Well, the key insight in Ebrahimnejad et al. Is that if you multiply the input matrix A by these two block Krylov matrices on each side, you obtain a block Henkel matrix. And that's very good because it's very structured. So a Henkel matrix is a matrix where each entry along the diagonal transposed is repeated. And in our case, it's blocked because U is a block vector. And so it's just the same thing, but blocks of size S by S. And so now we have managed to decompose an arbitrary matrix A, its inverse, into two Krylov matrices, which are very structured, as you saw, and the inverse of a block Henkel matrix. And so now the question of inverting A becomes a question of inverting a block Henkel matrix. So now we focus on the inversion of block structure matrices. And I will do this explanation with Toeplitz matrices just because the notation is easier. It's the same idea as a Henkel matrix, except the entries are repeated along the diagonal instead of the diagonal transposed. So it's clear that a Toeplitz matrix has a lot of structure, but what about the inverse? Well, unfortunately, if you try a simple example, the inverse is not Toeplitz, but we would hope that it still kind of retains some sort of structure by being the inverse of a Toeplitz matrix. That's exactly the question that Kailat et al. Were asking in the 70s and made them introduce a notion of displacement rank. So they said, okay, take a circle on matrix Z, which is defined as all zeros except this diagonal of ones. And the good thing of this matrix is that when you apply it from the left, you shift your matrix down and that becomes zeros. And when you apply it from the right, you shift your matrix right, and then that becomes zeros. And so you can see that by the structure of a Toeplitz matrix, these all become zeros when you subtract it from the original one. And so you get a rank 2 matrix. Okay, so that's not very surprising, but the very important thing of their paper is that the same thing happens to the inverse. So if you apply the same linear operator, actually the dual, we just need to shift C transpose and Z, which was Z and C transpose here. If you apply it to the inverse of a Toeplitz matrix, you also get a rank 2 matrix, which is very not obvious. And that's a general phenomenon. So we're going to call this a displaced matrix, means after we apply this operator, and the displacement rank will be the rank of this displaced matrix. And so Kailat et al. Showed that the displacement rank of a matrix equals the displacement rank of the inverse. And so in the case of Toeplitz and Henkel matrices, it's 2 in both cases. Now in their paper, they also tell us how to recover the undisplaced original matrix from the displaced matrix, because this operator happens to be invertible. And so let me display this theorem in a picture, which is clearer. So we have a matrix, then we apply the displacement operator, we get the displaced matrix, which has displacement rank alpha. And so because it has displacement rank alpha, we can express this matrix with alpha vectors, which we call generators. And then Kailat et al. Tell us that if we want to go back to the decompressed, like original undisplaced matrix, we take the entries in these generators, we place them in this upper and lower triangular Toeplitz matrices. So you see, again, it's repeated entries. And if we perform these alpha sums and the alpha products, and then we sum them together, we obtain the original matrix. So that's how we go from displaced to undisplaced. And this also really generalizes to the block size. In the block size, these vectors are size n by s instead of n by 1, but still it's a very succinct representation. Okay, so there's no inverse here. And so the natural question is, if you give me matrix A, how quickly can I find the rectangular generators of the inverse? And Bitmet and Anderson gave an algorithm for that in subquadratic time, which also extends to the block case. And so given a matrix A, we find the generators of the inverse. So now the question is, once this algorithm gives us these generators, how can we recover the inverse explicitly? And explicitly, I mean writing down all n squared entries. So let's go back to our setting where we had a block Henkel matrix. As I said, all these displacement rank approach generalizes to Toeplitz, Henkel, van der Waals, Cauchy, etc. And so with this Bitmet and Anderson algorithm, we can have the rectangular generators of our block Henkel inverse. But we want the Henkel inverse, and so we need somehow to go from these generators to the matrices that we actually want. Now the question is, how fast can we do that? And that's where we bring up the idea of fast rectangular matrix multiplication to multiply the compressed expression. So these rectangular generators, x and y. What happens if we just multiply these rectangular generators? We obtain this matrix, which is unfortunately not the matrix we want. That's the matrix we want, if you remember from the UL decomposition. However, if we look at this matrix, you will see that each entry of the matrix that we want corresponds to the sum of all the preceding entries in the diagonal of the matrix that we have. And so what we can do is we can use fast rectangular matrix algorithms by Legal and Urrutia to obtain this matrix. And then we build the matrix that we want by traversing the diagonals of the matrix that we have and filling up this matrix in a kind of recursive dynamic programming manner. And so for each operator, we can find this recursion that links the two matrices and takes only O of n squared time. So the general scheme is we have our block matrix that we want to invert, which is structured. We use the Bitmet-Anderson algorithm to find the rectangular generators. We use fast rectangular matrix multiplication to multiply those. And then we find the appropriate recursive formula to build back the undisplaced explicit inverse matrix. And so the key strategy is that we stay to work with a compressed linear expression for as long as possible. And if you check the theorems that we have for this construction, we get quadratic time exactly for inverting a block Henkel and Toeplitz matrices for blocking factors S up to a range. And that's the best we can do because just writing down the matrix takes O of n squared. So quadratic is the best we can hope for. So let's go back to our setting. Now that we know how to invert the block Henkel matrix, we remember that we had the expression, we had decomposed A inverse into this 2 Krylov and the explicit block Henkel matrix. So what remains to obtain A inverse is just to apply the block Krylov matrices to this block Henkel inverse. And we can do that efficiently using Horner's scheme given the structure of these Krylov matrices. And so that gives us the inverse of A. And well, we get an expression that I won't get into, but basically if we optimize this expression for the block size S, that's where we obtain the final runtime of O of n to the 22131 for sparse matrices, which yields the fastest known runtime. And a very neat thing about this runtime is that it ends up only depending on the value of rectangular matrix multiplication. So this black line corresponds to the current values of fast rectangular matrix multiplication by Legal and Urrutia. And this black dot is where the runtime for sparse matrix inversion happens. And you see that it happens, if this value is lower, then the value for sparse matrix inversion is also lowered. So I will conclude with some remarks after this overview of the construction. The main takeaways would be the interplay between finite fields and finite precision arithmetic algorithms and how we can have insights in both directions. The idea of decomposing arbitrary matrix into structure ones, such as Krylov and Henkel. The use of displacement operators when we work with structure matrices. And the use of fast rectangular matrix multiplication when we work with these compressed bilinear expressions. And if you're interested, you can check the extended work on arXiv. And thank you very much for your attention. Thank you also to the session chair and to the organizers of ITCS for making the conference possible. And now I'm happy to take any questions.
Okay, thank you for the talk, Sílvia. Very interesting. Feel free to unmute yourself or, yeah. Yeah, go ahead if you have any question. Maybe I have one question. Maybe it's a dumb question. I'm a little bit confused. Like, it seems to me like the algorithm didn't use the property that the matrix is sparse crucially. I just wonder, like, if the matrix is dense, like, what will be the bound, or like where the argument will break down? Maybe that, yeah.
Yeah, that's a very good question. I mean, I cut the explanation of the construction because it was only 10 minutes, but basically the sparsity is crucial when we build the Krylov matrices and when we build some other matrices. Basically, when you need, so let me go back to the first construction, which is here. If the matrix is dense, then you can't build these columns efficiently. The way they're built is by successively applying A, and when A is sparse, meaning it has like O of n non-zeros, then applying it to a vector only takes O of n. But if it's dense, it will take O of n squared, and so then it becomes too expensive to build these Krylov matrices in the first place. So you're right that it does not affect the inversion of the Henkel matrix. Like regardless of A being sparse or dense, you can't say anything about the inverse of the Henkel matrix, but you need it to build kind of the matrices that allow you to do this decomposition. But yeah, that was a very good point.
Okay. Yeah, thank you. Okay, if there's no other question, let's thank the speaker again, and yeah, thank you so much. Okay, the first talk. Okay, Steve, do you want to share your screen? You are muted. All right. Okay, let me make the introduction. So hello everybody, we will have the fourth talk in this session by Steve about uniform bounds for scheduling with job size estimates. Here you go, Steve.
All right, thanks, Xue. So hi everyone, I'm Steve. I'm in this last year of my PhD at CMU. And today I'm going to tell you about some joint work I've been doing with Isaac Grosof and Michael Mitzenmacher about scheduling with noisy information. And so At a high level, this work lives in the world of algorithms with predictions, and specifically scheduling algorithms with predictions. So we've got a bunch of jobs in a queue, and we're trying to decide which job to serve to minimize average delay. And the type of predictions we're working with are job size predictions. So it's generally good to serve short jobs, small ones, ahead of large jobs. The idea is you can get something done as quickly as possible, and this ends up being good for average delay. But this is hard to do when you don't know how big job sizes are. And so if you have only noisy predictions of job sizes. So that's the problem we're studying. And one twist about this work is that we're doing this all in a stochastic setting. So we're kind of taking a stochastic first mindset. There's like a sprinkling of worst case, but mostly stochastic. And our motivation for this is that lots of computer systems in practice are well modeled by stochastic arrivals. And so we hope studying this setting will give the right insights for scheduling in practice. So the question we're studying today is, how do we schedule to minimize delay with noisy size estimates? So let me start by taking apart this question. What do I mean by scheduling and delay? What sort of assumptions are we going to make on the noise around the size estimates? And what do I mean by minimize? What's a reasonable goal to hope to achieve? So I'm going to answer all of these questions in today's talk. So let's start with what are scheduling and delay. So basically, what is the setting of our problem? So this is a single server queue. So this is a server. It does some sort of useful work. This is a queue which holds jobs waiting for service. And this is a job. I'm going to draw it as a test tube whose height is its size, the amount of time it needs to be served. And so I'll represent that service as filling the job with water. And so we can talk about the remaining size of the job, the amount of work left, or its age, the amount that's been done so far. Okay, and so we have these jobs stochastically arriving over time. And I'll just flash the assumptions of the arrival process. The only one I want to point out is this job size distribution. So each job size is generated IID from some distribution, but I'm not going to make any assumptions about what this distribution is. It could be anything, which is important because in different systems in practice, they have very different looking job size distributions. Okay, so this is our stochastic queuing model. So at some point, the server is going to finish this job. When the job is done, its age equals its size. It exits the system. The amount of time this job spent in the system between arrival and completion is called that job's response time. So whenever I say delay, I'm talking specifically about response time. So that job is gone. The server's empty. What does it do next? This is the domain of the scheduling policy, which decides at every moment in time which jobs to serve. And it does so preemptively. We can interrupt one job if we get bored of it and start serving another one. And we're going to assume no overhead or other funny business when we preempt. Okay, so this is scheduling in the stochastic queuing world, and we're trying to optimize delay. So what does optimizing delay mean? Well, I told you that delay is response time, the time between a job's arrival and departure, but I've got a whole bunch of jobs arriving to the system. So I'm not just going to look at one job's response time. I'm going to look at the response time distribution over all jobs in some very long arrival sequence. And this distribution will be affected by the scheduling decisions we make. And so our goal today is to design a scheduling policy that minimizes mean response time, or at least gets it as low as possible in some way. So as a warm-up, how should we schedule if we know job sizes exactly, if there are there's no noise at all? And so, well, I told you earlier that it's generally a good idea to serve short jobs ahead of large jobs. The policy that takes this to its natural conclusion is called SRPT, shortest remaining processing time. And this always serves the job of least remaining size in preemptive fashion. So if a short job arrives, it'll switch to that short job. So that's if we have perfect information. What if we've got noisy information? So that's what we're studying today. So when a job of true size S walks into the system, we as the scheduler learn only a noisy estimate of that Z. And so what assumption are we going to make about how Z is related to S? We're going to assume that Z is within some constant factors of S. So beta below and alpha above. And I told you we're in the stochastic queuing world. And so these pairs of a job's true size and estimated size are going to be drawn from some joint distribution. Okay, but other than assuming this beta alpha bounded property, I'm not going to make any assumption about exactly how S and Z are correlated. Maybe for some size, it's always an underestimate. Maybe for other sizes, it's always an overestimate. And we're going to try and schedule in a way that gets good mean response time no matter what this joint distribution is. And in fact, we're also going to try and do it without knowing what alpha and beta are. So this is a sort of semi-adversarial problem where we can say an adversary is choosing the noise model. It's going to be beta alpha bounded, but it's choosing the noise model. And we, without knowing the exact distribution they chose, without knowing what alpha and beta are going to try and achieve good performance. And so that's the noise model we're considering. So what can we hope to achieve in this model? So this is algorithms with predictions. And so the kind of two main games in town are consistency, which is good performance under low noise, and robustness, which is good performance, or at least good enough performance under really bad noise. And unfortunately, it turns out you can't achieve robustness, at least not with constant R in our setting. And so we can't hope to achieve good mean response time within a constant factor of SRPT for arbitrary alpha and beta. So what could we hope to achieve instead? Well, we can still hope for consistency, but what if we have, alpha and beta, they're not super close to 1, but they're not super terrible either. What if we've got medium noise? So we introduced a property which we call G graceful degradation, or just G graceful for short, where a job's approximation ratio is bounded by some constant times a measure of the estimation, which in our case is the ratio alpha over beta. That's the kind of natural measure of estimation error. And so we can hope for consistency, and we can still hope for G gracefulness, this sort of medium noise good performance. And I'll say that G gracefulness is not like a totally new idea, but it's maybe a new-ish idea to at least call it out as being as important as consistency and robustness. So there is work that studies G gracefulness, sometimes other names, sometimes it's called robustness, just makes it more confusing. But I think it's important to kind of study this medium noise setting as well, and to start adding this to the set of things we sometimes think about in algorithms with predictions. Okay, so we can hope for consistency and gracefulness, and that's exactly what we achieve. We introduced the first scheduling policy for the stochastic scheduling setting that is consistent and graceful. So the policy itself is new, as is our analysis of it. And something I'll point out here is that this consistency result with C equals 1, perfect consistency as the noise decreases, that's impossible to achieve with worst case arrivals. And so that's an interesting fundamental difference between stochastic scheduling and worst case scheduling. And so I think it's exciting that we have both kind of perspectives working on these sorts of models at the same time. Okay, so in the last kind of 2-ish minutes of the talk, let me give you a bird's eye view of what our policy is and how we analyze it. So I'm not going to be able to totally describe the policy, but at least be able to draw a picture of it. And so I'll start by drawing a picture of SRPT as something that we call a rank function. So SRPT is always serving the job of least remaining size. So what the rank function does is it sort of encodes that prioritization policy as a function. So a job walks in, and its priority is going to be its size, and lower rank means better priority. And so under SRPT, as a job's age increases, its remaining size decreases, and it gets better and better priority. So that's SRPT's rank function. So what we figured out how to do was we figured out a rank function that approximates SRPT's rank function, but with only knowing Z and without knowing S. And so there was some trial and error in generating this, which I'll mention at the end of the talk. But we came up with this policy, which we call radical, because it kind of looks like a square root sign, vaguely. And this is the policy that's consistent and robust. But it turns out to be really hard to directly compare radical to SRPT. And so what we do instead in our analysis is we go via a third policy called scale. And scale is sort of a direct sort of SRPT, but where the job's rank, instead of starting at its true size, starts at its estimate size. You can't actually implement scale without knowing true sizes. So it's just a tool for analysis. But it turns out we can compare radical to scale and scale to SRPT. All right, and I'll mention one more thing about our analysis, which is how do we do each of these comparisons? And this is where the second sentence of this talk comes into play. I'm in the last year of my PhD. So my thesis is all about analyzing the performance of scheduling policies in these sort of stochastic settings and expanding the reach of what scheduling theory can do and queuing theory can do. And so there are two main things in my thesis, and I'm excited about this paper because it gets to use both of these things, which is the first time we've had to do that. So the first kind of piece of my thesis called SOAP, which we use to compare radical to scale. And then we use the second piece of my thesis, which is called Wine, to compare scale to SRPT. So these are both kind of new ideas from queuing theory. And one thing I'll mention is that Wine, as I'll explain in the full version of this talk on YouTube, also could apply in worst case scheduling. So that's kind of what I want to highlight that. All right, so what did we talk about today? So we talked about scheduling with noisy information. We introduced a new policy that has provably good performance, and we managed to do that proof by combining these two new ideas from queuing theory. And one thing I didn't get to talk about today, in the short version, but which you can find in the full version of the talk on YouTube, is why this problem is hard. And the reason this problem is hard is because the first ideas that you would think of for approximating SRPT's rank function turn out to have poor performance. All right, so that's what I wanted to say today. I'm happy to take questions, or you can get in touch by email. Thanks for your attention.
Thank you for the talk, Steve. So feel free to unmute yourself or leave your question in the chat box. So maybe I have one question to you. So you mentioned like the problem is fundamentally different in the worst case, right? Like you are dealing with the stochastic setting, and you say the problem is extremely hard. Can you spell out that, or like elaborate more on so what is it? So is there no constant approximation for the worst case? Yeah.
So I think in the worst case setting, they're actually, so the same group published one thing and then they published this follow-up. So I forget the exact state of the art, but I think they prove something that is roughly equivalent to our, I forget if it's alpha over beta or alpha over beta squared factor. So they basically prove graceful degradation. So that is possible in the worst case setting. What isn't possible is this perfect consistency. It turns out you can't do better than C equals 2 in the worst case. Grace and another kind of important difference is that the sort of algorithm that you need to use in the worst case is much more complicated, right? Here we have, I can draw a picture. It's basically saying, this is how you prioritize a job over time. And that's enough for the stochastic case. There's still a lot that goes into the analysis, but the policy itself is very simple and is sort of simple enough that you could actually use it in practice. And in the, yeah.
Cool. Yeah. Thank you for the thank you for the answer. Okay. If there's no other question, let's thank the speaker again. Okay. So now it's the last talk by Ansh. Do you want to share your screen, Ansh?
Yeah. Can you see my screen?
Yeah. It's cool. It's good. Yeah. Okay. So hello everybody. So this is the last talk in this session by Ansh about the counting and sampling perfect matchings in regular expanding non-bipartite graphs. Okay.
Okay, thank you. Yes, I'll try to finish by 2:30. So hello everyone. This is our paper on counting and sampling perfect matchings. And this is joint work with Farzam and Cheyenne. So let's start with some notations. Let's say G is a graph with an even number of vertices equal to 2n. I'm going to use m of I to denote the set of all matchings containing exactly I edges. And little m of I is going to be the cardinality of the set. And I guess two examples are when I is equal to n, we call these the perfect matchings. And when I is n minus 1, we call them the near perfect matchings. So take this graph, for example. It has exactly 2 perfect matchings. So little m of n is equal to 2. And the main algorithmic task we're going to be concerned with in this talk is, can we compute the number of perfect matchings? It was shown by Valiant that it's sharply hard to do this computation exactly. So we are going to have to settle for an approximate computation. And I guess one of the main ideas that's being used for this task is the following equivalence proved by Jerem, Valiant, and Vazirani in much more generality. So the equivalence states that the existence of a efficient randomized approximation algorithm for the number of perfect matchings is equivalent to the existence of an approximate sampling algorithm from the uniform distribution over all the perfect matchings. And here are 2 of, I guess, the major results that have used this equivalence. So the first result is by Jerem and Sinclair, who give efficient algorithms who give Markov chain based algorithms for the task on the right, which gives an efficient algorithm for the task on the left, as long as the ratio of the number of near perfect matchings to the number of perfect matchings is bounded by some polynomial. The second result is by Jerem, Sinclair, and Vegoda, who give similar algorithms, Markov chain-based algorithms that are that work in polynomial time if G is bipartite without any more restrictions. And let me just state that we know that there exist graphs, even bipartite graphs, for which the ratio of near perfect matchings to perfect matchings is exponentially large. So it's not quite trivial to see how many graphs kind of fall under the first result. And indeed, this is a result that we are going to be using later on in this talk. And one of the biggest open problems in the field is, can we do these tasks for any graph, not just the ones tackled by these results? Okay, and I guess our first result is that we can do these for a certain class of graphs, which are the D-regular expander graphs. So let me define what an expander graph is. For simplicity, let's just say that the graph is D-regular, and let A tilde be the normalized adjacency matrix. We know that A tilde has a trivial eigenvalue of 1. And we're going to say that the graph is an epsilon spectral expander if every other eigenvalue has magnitude of at most epsilon. And for example, Friedman proved that almost every D-regular graph has epsilon, which is around 2 over square root D. So now I can state our first result, which is if G is a D-regular epsilon spectral expander, then there is a algorithm for approximate sampling and counting the perfect matchings that runs in time n to the log D over log 1 over epsilon. So to make sense of this, notice that if epsilon is small enough compared to D, or if D is a constant, then this is a strictly polynomial time algorithm. In particular, using Friedman's theorem, we can prove that this gives a polynomial time algorithm for almost every D-regular graph. Yeah, I guess one thing to note is that these results should also hold if G has all of its degrees in theta of D, as long as the spectral expansion is good enough. And one caveat of this result is that we require epsilon, the spectral expansion, to be less than this constant. And this is only achievable if D is larger than some fixed constant. So in particular, this theorem doesn't say anything for 3 regular graphs. Okay, now let's switch gears and talk about a different kind of result you can prove about perfect matchings. So the van der Waals conjecture, which was proved by Felikman and Igorichev, says that if G is a D-regular bipartite graph, then the number of perfect matchings is at least D over e to the n. It's natural to wonder whether you can construct an analog for non-bipartite graphs of this theorem. So Loash and Plomer conjectured that something similar holds. As long as D is a D-regular graph, that might not be bipartite, but it has edge connectivity of D minus 1, which means the minimum cut is at least D minus 1. And this conjecture is still open as of now. And the best bound we know is to show something like these kinds of graphs have the number of perfect matchings that is at least 1.001 to the n. Ideally, we would like to show something similar like D over e to the n, like was the case in van der Waals conjecture. Okay, and actually, we also know some lower bounds for random regular graphs. And there's a result of Bolobash and Megow, which shows that with high probability with respect to the degree, the number of perfect matchings in random regular non-bipartite graphs is approximately D over e to the n. So here's our second result. We show similar kinds of lower bounds for D-regular spectral expanders. Notice that this second term, it's like an error term, which is going to be negligible to the first term when epsilon is small enough. So one can view our second result as some kind of special case of the Loash-Plomer conjecture. If you view expanders as a special case of edge-connected graphs. And one can also view our result as a kind of strengthening of Bolobash and Megow's result. So let me tell you the main ingredient of our proof. The kind of inequality that we show is that for every k, the number of k matchings, the ratio of the number of k matchings to the number of k minus 1 matchings is bounded by this quantity on the right. And I guess for some intuition, you can plug in k to be n-1, and it gives you that this ratio is bounded by n to the log d over log of 1 over epsilon. And recall that this was exactly the running time of our algorithm from before. Let me skip this. And it turns out that we can use this lemma to prove both of our results. Yeah, I guess in the interest of time, let me also skip the how these results are proved from the lemma. And let me tell you a few things about how to prove this lemma. So let's assume k is n-1 to simplify the lemma. It turns out that this kind of lemma has been studied before in bipartite graphs by Jerem and Sinclair and some others. And they show that the lemma can be reduced to this other argument, which says that for any near perfect matching in the graph, there is a short augmenting path with respect to that near perfect matching. So if we can show the bottom lemma for every graph that is a expanding regular graph, we would be able to prove the lemma on the top. Okay, and recall that an augmenting path for this near perfect matching is just a path that looks like this. It turns out in the bipartite case, we can use vertex expansion of this graph, along with a simple alternating breadth first search argument to show that I'm not going to go through the argument right now, but we can use it to show that there is indeed a short augmenting path in this graph. And the main difficulty comes in the non-bipartite case. It's not so clear how to emulate these arguments in that case. And that's our main technical contribution. So we try to perform the same analysis, the easy analysis for the bipartite case on a random bipartite subgraph. And that is the key idea of our proof. So we are going to construct a random bipartite subgraph that still contains the matching M. So as long as we are able to show that the subgraph has an augmenting path for M, a short augmenting path for M, this would also imply that the original graph has a short augmenting path for M. And this analysis is a bit tricky, but we are able to do it. And that is how we prove this lemma. Let me tell you about some future directions to think of. Two of the main directions that would be interesting is whether we can prove similar results with weaker expansion guarantee. So for example, if the graph is only a one-sided expander, or if the expansion is closer to 1 than to 0. And another conjecture is whether we can prove something using conductance of the graph instead of spectral expansion. A third idea is maybe we can use this idea of random bipartitions, random bipartite subgraphs algorithmically, and maybe you can reduce counting the number of perfect matchings to counting the number of perfect matchings in a random bipartition, which we can already do by Jerem, Sinclair, and Vigbora's algorithm. And obviously, the last future direction is Lowash-Plummer conjecture. And let me just say that another interesting result we could get out of analyzing the Lowash-Plummer conjecture is potentially better algorithms for computing perfect matchings in the case of deregular T-1 edge-connected graphs, which would be pretty interesting. Okay, yeah, let me stop there. And thank you to the chair, and thank you for everyone for listening.
Yeah, thank you for the talk. Let me ask one. Does anybody have any question about for Ansh? Let me ask one question. So Ansh, so you mentioned like so you correct me if my understanding is wrong. Like so you mentioned the conjecture in the last page, like the m minus 1 dividing by mn, it could be something like n to the conductance, which could be super polynomial, right?
Yeah, it could be.
So then like it doesn't give you the polynomial time algorithm directly, right?
It does not give you a polynomial time algorithm for all graphs. So these directions are just exploring whether you can get polynomial time algorithm for expander graphs.
Okay. So if I want get a polynomial time algorithm, like is there any ingredients to solve that issue, or like we should have a new framework?
Yeah, it doesn't seem that this idea of bounding the number of this ratio of near perfect matchings to perfect matchings is going to get you a polynomial time algorithm in all cases. So we know for sure that there are many kinds of graphs that for which the ratio is exponential. So yeah, I think we definitely need new ideas for the general for every graph.
Okay, thank you. Okay, is there any other questions? Okay, let's thank all speakers again.
I have a, okay, sorry.
Yeah,
I had a question.
Sure.
So you mentioned the idea of like using the random bipartition algorithmically. So my first question was, so I guess my main question is, so is that part of the algorithm that you use, or is it only part of the analysis? Right.
Yeah, I should have said that. So the algorithm we use is the algorithm of Jerome Sinclair. Right. They gave an algorithm which works whenever the ratio of near perfect matching to perfect matching is bounded. And basically all we do is we show that for this class of graphs, it is bounded.
Okay, cool. Thanks.
Okay, okay, so I think that's all the questions for Ansh. Okay, so let me thank all. So let's thank all speakers and thank everybody come to this session. We have so I think we have 5 great presentations this afternoon. Okay, so thank all the speakers.
Thanks.
Hey Mark, do you have anything? Do you want to say anything?
Thanks for sharing, and see you tomorrow. We're starting, I believe, 10:30 Eastern. A little early Pacific, but 10:30 Eastern is session number 19. See ya.